All right, so now we're going to look at the formation of imines using aldehydes or ketones and a primary amine. So if we have an amine, let's start by talking a little bit about amines. There are three different classes of amines: primary, secondary, and tertiary. A little bit later, when we get to the chapter on amines, we will discuss this in more detail, but a primary amine is an amine that has one alkyl group on it. A secondary amine has two alkyl groups on it, and a tertiary amine has three alkyl groups. I make this distinction because this is different than all the other things. Like for alcohols, a primary alcohol, it's not how many carbons are attached to the oxygen, it's how many carbons are attached to the carbon that the OH is attached to. So for amines, it's a different way of classifying things. If we treat an aldehyde or a ketone with a primary amine, we will get a compound that is called an imine, sometimes called H-Schiff's base, but we will get an imine. And so here is an example. We've got either an aldehyde or a ketone, and then we have a primary amine in mild acid. Turns out that mild acid is very important. If it's too strong, it doesn't work. If we don't have acid at all, it doesn't work. So that will form the carbonyl amine, which will then decompose to give us the imine. So we'll lose water. So let's look at what's going on. Well, first, let's talk about imine properties. What makes imine? Imines, in a lot of ways, behave like carbonyls. And that's because we've got an electronegative group. We've got an electronegative group that is in a double bond with carbon. Right, and it is subject to nucleophilic attack like carbonyl compounds are. However, it's also different in that we've got something else that is attached to that nitrogen. Instead of having two lone pairs like we do on the oxygen, we're going to have one lone pair and one atom attached. That atom can either be a hydrogen, if it were ammonia, or it can be something like this, where it's an alkyl group. Because it's sp2 hybridized, we're going to have an angle of 120 degrees, approximately 120 degrees, instead of 180 degrees. Here is another example of a primary amine reacting with acetone, and we get this imine. All right. We'll find that imine formation occurs when the reaction medium is just a little bit acidic. And I mentioned this a minute ago. If it's too acidic, it doesn't work. And if it's not acidic enough, it doesn't work. The key is that we need to have some of our base, which acts as the nucleophile, and we need to have some acid because we need to protonate things. And if we don't have both of those, in essence, if we don't have a buffer solution, essentially, then it's not going to work. So let's look. So imine formation mechanism. So here are the steps for imine formation. First, we'll get nucleophilic attack. Here we've got this primary amine that comes in, attacks that carbonyl. And when it does, we're going to form this sort of weird looking intermediate. Now, the next step is written as proton transfer. And you'll notice there are no arrows. I kind of don't like it like this, but that's okay. Really what needs to happen is something needs to come in and deprotonate this NH2+, and something else needs to come in and protonate this. Whether it's this hydrogen or not, we don't know. I mean, you can make it so that it is not. I mean, you can definitely make it some other hydrogen has to protonate this, but the point is that this is a little more complicated than just proton transfer. In any case, we form a carbonyl amine, and in the presence of acid, we can protonate that OH. All right, we protonate the OH there, which will give us H2O. All right, and when we get that H2O, the H2O plus is a good leaving group. So we'll lose H2O plus to form a resonance stabilized iminium ion. All right, and then something that's present in the solution, for example, water, will come along, deprotonate that, and give us our imine. And that's how we form imines from primary amines and carbonyl compounds, in particular, aldehydes and ketones. Let's go over and look at 21. So we need to determine what primary amine and carbonyl compound is needed to prepare each of these. This is pretty easy. It's kind of like when we were doing the Wittig reaction a little bit earlier. We can come in and just sort of slice this. And so if we slice this, we say there, and I'll go ahead and do this one. So find the double bond between the carbon and the nitrogen, the one that you're trying to make, and that way you can figure out what components you needed to make it. The thing that is on the nitrogen side, that will be the amine, and the thing that's on the carbon side, that will be the carbonyl compound. So in this case, our carbonyl compound, and I'm going to write this sort of as a retro synthesis, our carbonyl compound is going to be acetaldehyde, and our amine is going to be propanamine, so H2N. We get that. For this one, we'll see that we have this cyclohexanone derivative will be our carbonyl compound, so it'll be a ketone. All right, so that will be this part, and then the amine part is going to be aniline. All right, and that is number 21. So let's go back and look at the next thing. So there are amines that show up in nature, and when they show up in nature, we will end up, we can form these amines. Let me just show you an example. So there's a compound called cis-retinal. Cis-retinal is it's in the family of vitamin A. There's retinol, where this is an OH, and there is a bond that we can convert between cis and trans. I'll talk in a minute about how that happens, but if we have this in the form of cis-retinal, that cis-retinal can react with a protein that's called the opsin, and we can get what we call rhodopsin. This rhodopsin is very light sensitive, so it's very, very light sensitive. This is inside the rods of your eyes. The rods are the component of your vision. So there's rods and cones, and the rods are the component of your vision that help give you low light vision. And so this molecule is what makes it possible for that low light vision to occur. So what happens is when this molecule, I'm going to go to the next page here, when it is exposed to a very small amount of light, it will undergo a isomerization. It will go from the cis form to the trans form and release a little bit of energy. And that little bit of energy, through a complex series of events, gets translated as a impulse in your nerves and gets sent to the brain as, hey, a photon. Okay. So now, once that happens, this molecule is not going to do that again until it gets converted back into the retinal that we saw on the previous page. So what has to happen is that this gets hydrolyzed. It gets converted from the retinal to the retinol, from the retinol into an ester, and I'm trying to remember the exact series of events, but there is a protein that will convert that back into the cis isomer. And when it gets converted back into the cis isomer of the retinal, then it can be used again. So it gets cycled over and over again. One of the cool things about this is that you only have a certain number of these opsins in your rods. And so there's only so many signals that you can send. If you're under low light conditions, then it absorbs a photon, it sends a signal to your brain, and so you can see things when it's fairly dark. If you have, let's say you're in the dark inside your room, and you can see things pretty well, if you turn the bright lights on, so you turn the overhead light on, maybe your side table light, you turn those on to so that it's bright in the room, it's going to saturate all of these and convert them all into the trans form. And that means when you turn the lights back off, you're going to have more trouble seeing in the dark because you don't have any that are in this cis form ready to communicate to your brain. So, and it usually takes your eye about 30 minutes to completely regenerate these and get them ready to go again. So this is why you don't have great low light vision after the bright lights have been on. So you get what you call night blindness. Now, one more thing I'm going to mention, and then I'm going to move on from the biochemistry stuff. And that one more thing is that you get the retinal, you get that from consuming things that are in the vitamin A family, which includes the retinal, the retinol, the retinoic acid, and carotene, beta carotene. When you consume those things, you can produce more of this and you will have good night vision. If you do not get enough of that, if you have a vitamin A deficiency, one problem that you can have is you can have poor night vision because you don't have enough of this chemical. And you can get too much of this chemical. You can get too much of the retinal, but usually if you eat things like fish and meat and milk, dairy products, you will get some of this vitamin A, and you will you should have enough. So again, I'm not going to encourage you to take a vitamin A supplement. I would talk to your doctor or dietitian about that. So now let's look at what happens when we have secondary amines. It's something different because we don't have enough hydrogens to form an imine when we do this. So same first step or same process here. We convert from this to the carbonylamine, and that loses water. But instead of getting a carbon-nitrogen double bond, we end up getting a carbon-carbon double bond. Let me show you some specific examples here. Here we have cyclohexanone plus this secondary amine, and we get this. Again, this is called an enamine. Here's another one, acetone, with this cyclic amine, and we end up getting this enamine. All right. One key feature that the ketone or aldehyde must have for this to work is that there must be at least one alpha hydrogen on the alpha carbon. If you do not have an alpha hydrogen, you can't do this. Now, fortunately, most aldehydes and ketones are going to have that alpha hydrogen, but it is possible in certain situations not to have that, in which case forming an enamine would not be possible. Let me show you the mechanism for enamine formation, and then I will emphasize that again. When it comes to the mechanism, the first step is just like the first step of imine formation, which is we get nucleophilic attack of our amine on the carbonyl compound. So nucleophilic attack. That nucleophilic attack, when it happens, we get this intermediate, which we have to do proton transfer, which I should probably put that in quotes because it's a little bit. I mean, we do transfer a proton, but is it the same proton? I don't know. So we will get this carbonyl amine. That carbonyl amine will then get protonated by the weak acid. This is why we have to have weak acid in solution. It needs to be basic enough that we have this, and it needs to be acidic enough that we have something to protonate with. So we protonate that, and when we protonate that, we will get this H2O+, which acts as a leaving group. So we lose that, and we'll get a resonance stabilized iminium ion. And then instead of deprotonating the nitrogen, we end up deprotonating the alpha carbon, and we get an enamine. And that is our mechanism for enamine formation. Now, just to look at the tiny details here of the imine versus enamine formation, with the imine, right, when we have a primary amine and we form an imine, what happens is we get to the step where we have the iminium ion and we can deprotonate the nitrogen because there's still one nitrogen left over. When we have a secondary amine and we react that with our carbonyl compound and we get to the iminium ion, there's no hydrogen on the nitrogen to deprotonate. So that's why we have to deprotonate at the alpha carbon, and we end up with that carbon-carbon double bond. So let's look at number 22 real quick. And on this it says, what two enamines are formed when 2-methylcyclohexanone is treated with dimethylamine? So let's go ahead and draw our ketone. So there is 2-methyl, the 2-methyl cyclohexanone, and then the CH3-2NH, and we'll say with mild acid, if we're just going to go ahead and get this all correct. So mild acid. When we do that, we are going to get a new carbon-nitrogen single bond. All right, our methyl will still be here. We'll have a carbon-nitrogen single bond, so CH3, CH3. But we can't remove a hydrogen from there, so we end up forming a double bond between the carbon that was the carbonyl carbon and the alpha carbon. In this case, there are 2 possibilities. We can do it here or here. I will draw the other one as well. And we will get that enamine. All right, so that is those are the 2 products that we will get with this particular set. It's not uncommon to have 2 different possibilities when we are doing this. So now let's look at hydrolysis of imines and enamines. It is possible to do hydrolysis of this. All of the reactions that are in that mechanism that I showed you are reversible. So we can take it and go back the other direction. And the key to this is that we just need to have water present in doing this. So when we form the imine and enamine, we end up losing water as one of our mechanistic steps. But if we have excess water present, then we can reverse it, and we can get our original carbonyl compound and our original amine. And that works for both the imine and the enamine. So now let's look at addition of H2O, which we'll call hydration. We add H2O across a carbon-oxygen double bond, in particular an aldehyde or a ketone. So if we treat that aldehyde or ketone with water in the presence of either acid or base, we can get what is referred to as a CHEM-diol. So a CHEM-diol, and CHEM just means geminal diol. It means that we have the 2 OHs on the same carbon. Sometimes you'll see this referred to as a hydrate, and sometimes you'll just see it referred to as the diol, but it's a CHEM-diol, a hydrate, that all means the same thing. Now, not all of these do this to an equal extent. And so if we've got formaldehyde, for example, and we treat formaldehyde with water, again, in the presence of a small amount of acid or base, we can form the formaldehyde hydrate, which is just methane diol. In fact, if you've got a bottle of formaldehyde that is that's dissolved in water, and we just call that formalin, if you have formaldehyde dissolved in water, it's mostly in the form of the formaldehyde hydrate or methane diol. There is another chemical. This one is, if it has an electron withdrawing group on adjacent atoms, it will also make it more likely to form the diol. By the way, this is called chloral, and this is chloral hydrate. And chloral hydrate, if you've heard of the term slipping a Mickey, this is where nefarious people will, while you are not looking, put a sedative into your drink, and then when you drink it, you lose control. And so this again is a pretty horrible thing to do. This is why when you go to a bar and there are lots of people there, you need to be aware of who is near your drink, and you never leave your drink unattended. If somebody slips this in, you could get hypnotic. You could get very tired, sedated. It's a sedative effect. So anyway, you got to watch your drinks. And if you are a person who's ever done this to somebody else, that means that you are a horrible person. Just keep that in mind. You'd be a horrible person. So don't do this to other people. And watch out for your friends. And watch out for people who are not your friends as well, because nobody deserves that. Oh, and by the way, that's illegal. So you'd be a horrible person and a criminal. All right, enough of that public service announcement. So watch out for chloral hydrate. Hydration levels. So how much of the hydrate is formed? Well, it depends. It depends on what things are attached. If you have hydrogens attached, like we do in formaldehyde, essentially all of it is going to be in the form of the diol. So as I mentioned, if you have the formaldehyde solution, almost all of it will be in the form of methane diol. If you've got an aldehyde that's got an alkyl group, well, alkyl groups add electron density, helps to stabilize the positive charge on the carbonyl carbon. Then you'll get not quite as much. So you'll get less of the hydrate. Although with acetaldehyde, that's still a significant amount. And then if you have acetone, which has two alkyl groups, the two alkyl groups will make it so that hardly any of it, only a small fraction of a percentage of it, is in the form of the hydrate. So it really depends on what's attached. Formaldehyde does it the most. Aldehydes, particularly aldehydes that have electron withdrawing groups on the adjacent carbon. As I mentioned, chloral has these electron withdrawing groups that makes a significant partial positive charge on this alpha carbon, which pulls electron density away from our carbonyl carbon, making it more susceptible to nucleophilic attack, and that increases the amount of hydrate. Let's look at number 25. This is a ranking question, so this one will go pretty quick. Right. We want to rank these in order of increasing percentage of hydrate formation. So here we have an aldehyde with some electron withdrawing groups. Here we've got a ketone and then an aldehyde. The ketone is going to have the lowest. So we're going to put B has the lowest percentage of hydrate formation. Next is going to be this aldehyde. So we'll put C for that one. And then the one that has the most is going to be this aldehyde with the electron withdrawing groups. So we'll put A there. So least and most. We can also do base-catalyzed hydration. And so with base-catalyzed hydration, we will have our base hydroxide act as a nucleophile. That nucleophile is a pretty good nucleophile, so it comes in, reacts, and we get this intermediate, which is quickly protonated with excess water that's hanging out in solution. And so if you put base in there, you can increase the rate of CHEM diol formation. So because the hydroxide is a good enough nucleophile to help you do this. Now, what about acid catalyzed? Well, for acid catalyzed, there are 3 steps. These 3 steps are exactly the same 3 steps that we had when, well, they're exactly the same 3 steps we're going to have when we look at acetal formation here a little bit later, or hemiacetal formation. I was getting ahead of myself. So the 3 steps are this. And, you know, whenever you have acid catalyzed anything, pretty good bet that the first step is going to be protonate. So if you have acid catalyze something, protonate. So here we have our acid, and we protonate our carbonyl with that acid. That gives us a resonance stabilized carbocation, makes that carbon a little bit more electrophilic. And so now our weaker nucleophile, water, can come in and react with that electrophile. And when it does, we will make this intermediate. This intermediate just needs to be deprotonated, and that will give us our CHEM diol. So you can see we can do this with either acid or base, and it doesn't take a lot of acid or base to do this. A small amount will get the job done. All right, so now let's look at the addition of alcohols to do acetal formation. We're going to find this mechanism is very similar to the steps we just saw for hydrate formation. We can do what we call acetal formation. So if you have an aldehyde or a ketone and you react it with 2 equivalents, 2 molecules of alcohol, you can form an acetal. So here is an aldehyde or ketone. Again, aldehyde has at least 1 hydrogen, and with a ketone, they're both carbons. Here we've got two equivalents of alcohol. They can be anything from methanol, and there's some cool stuff we can do with this. I'll show you in a bit. We do need a small amount of a catalytic acid. Typically, we'll use something like toluene sulfonic acid. It's fairly acidic, but it helps with the solubility, and so it makes it possible to make this acetal. All right, and then here is an example of this. So here we've got the aldehyde. We've got two equivalents of alcohol. There's our acid catalyst, and we end up getting this acetal. Now, one thing I want to point out, a lot of people look at this and they say, oh, that looks like an ether. Well, acetals are not ethers. They are in a distinct category separate from ethers. So I want you to remember that they're not the same as ethers. They are distinctly different. All right, so now let's look at cyclic acetals. And so with a cyclic acetal, so if we have a diol like ethylene glycol, and so ethylene glycol is commonly used when making these cyclic acetals. You can use that in place of having two equivalents of an alcohol. Instead, have this ethylene glycol. You get a little bit of an entropy advantage over having two molecules of an alcohol. All right, so you have an entropy advantage. Like with the gem diol formation, it's reversible. So you can, if you want to, you can drive this reaction to the right by removing water. And if you want to drive this reaction to the left, you can add water. And it's really the same conditions will make each. So water is formed as a byproduct, and because it is a byproduct, we can remove it. We just need a clever way to remove that water. And there are a variety of ways we can do this, but I'm going to show you one of the clever ways we can do this. And then you may or may not remember this Le Chatelier's principle. Le Chatelier's principle says if you change something in your system, you have something that's at equilibrium, you come in and add something, it's going to push the equilibrium to the other direction. You remove something, it'll pull the equilibrium in that direction. So that's Le Chatelier's principle. Well, we can use Le Chatelier's principle by removing water to drive this reaction to the right. Let me show you how. All right, so this is called a Dean-Stark apparatus. The Dean-Stark tube is this, and so here we've got a round bottom flask, we've got our Dean-Stark, and then a regular condenser that has water coming in, water going out. And then in the Dean-Stark tube, there is a collector, a little reservoir where you can collect liquid, and then a little stopcock at the bottom that allows you to drain stuff out as needed. So let me show you how this works. So to use this to make an acetal, to help you drive the reaction to the right and remove that water, the trick is you put your carbonyl compound in here with benzene. And benzene's important in this case because benzene does something really unusual with water, and that water and benzene will both distill into the vapor phase at the same time. Even though water and benzene are not phase compatible, they are not miscible with each other, they will both get into the vapor phase at about the same temperature. So you've got benzene molecules and water molecules that are flowing up here, and then they hit this condenser, and when they hit the condenser, they will both turn into a liquid and drip down into this this reservoir, this collector. So you get benzene and water collecting inside of this tube. And when they collect inside of that tube, we're going to find that the water is more dense than the benzene. And because they're not miscible, they don't dissolve with each other, the water will be on the lower layer and the benzene will be on the upper layer. So you can just distill it over and you will start to build up liquid in here. And most of it will be benzene, but you will have some water in there. And periodically, you can just drain that water out. And when you do that, you are effectively removing water from the system. And you can just let this go over, and you can even let some of the benzene flow back over here and go back down into the flask because you don't want to remove your benzene. And so that it's a very cool method and a very clever method for removing water from a system. And really, the only downside to this is that benzene is kind of a not great solvent to use because of its toxicity and it's carcinogenic, but it is a very tried and true method for making acetal. So we probably wouldn't do this in an undergraduate lab, but this is something that would be part of a regular synthesis, a regular synthetic, procedure that you might do in an organic synthesis lab. All right, let's look at the mechanism, and I'm going to break it down into two parts. The first part is going to be the formation of the hemiacetal. And hemiacetal, hemi just means half. So the half acetal is where you have formed halfway to your acetal. So you have one OH and one OR present. Okay, so the first step is protonation of the carbonyl. If you have an acid catalyst, this is always the first step, is protonation of something. You will get a resonance stabilized carbocation that makes the carbon more electrophilic and makes the nucleophilic attack more possible. So your alcohol, which is not a strong nucleophile, will come in and react with that, and we will get this as an intermediate. We then just have to deprotonate that, and we have our hemiacetal. So that is how we form the hemiacetal. The next step is we're going to take the hemiacetal and convert that into an acetal, and that's going to take 4 steps. Now, I want to show every time you do this hemiacetal formation, you'll see that it's protonation, nucleophilic attack, deprotonation. That's the same thing we saw with our hydrate formation, right? Protonation, nucleophilic attack, deprotonation. Well, here, same thing. So let's look at converting the hemiacetal into the acetal. First step of this part is protonation. Again, not surprising. So we protonate. When we protonate that OH, we're going to get this where we have H2O plus, H2O plus, that makes H2O a good leaving group. So we'll lose H2O and we will form a resonance stabilized carbocation. That resonance stabilized carbocation can now undergo nucleophilic attack by our other equivalent of alcohol, and we will get this intermediate, and that intermediate just needs to be deprotonated. You can use the conjugate base of your acid, or you can use something else that's floating around in solution. I usually just use that conjugate base. That forms our acetal. So we are going to go through the mechanism of forming an acetal. So remember, protonation, nucleophilic attack, deprotonation, all right, all of those steps. And then we'll do protonation, loss of water, nucleophilic attack, deprotonation. So let's look at this particular one. So here we've got cyclohexanone, toluene, or not toluene, we do have toluene sulfonic acid, but we also have ethylene glycol, and then we form this product plus water. Again, if we want to drive this reaction to the right, we remove water, like with the Dean-Stark trap. So first step, we're going to protonate this. So I want to make sure I can fit this all on here, so I'm not going to draw huge. All right, so we'll have O, OTS, and we're going to protonate. So I'll do my little red arrow. We'll go from the oxygen to the hydrogen, and then those electrons will go over to that, and we'll have OTS minus. So this is what we have at this point. I'll put plus OTS minus. All right, and we have a positive charge there. We can draw a resonance structure for this, and I'm going to go ahead and do that. We'll kick that pair of electrons up to the oxygen. And we will get that as a resonance structure. All right, now we need our nucleophile, all right, because we've done protonation. Now let's do our nucleophile. And we just need a pair of electrons. Each of those has 2 pair we're going to have a nucleophilic attack of that alcohol on that carbon. And so when we do that, it's going to give us an intermediate. All right, and we'll get that thing there, and we still have a positive charge here. So we've done protonation, nucleophilic attack, and now we're going to do deprotonation. So we'll need something to come along, and again, I'm just going to choose the OTS minus as our thing to deprotonate. So OTS minus, so that's going to come in and deprotonate, and we will have a hemiacetal. All right, sorry about the size there. I got a little small. All right, so now what we want to do is we want to protonate that alcohol. So we're going to take a pair of electrons. We'll go from here to that H, and we'll protonate that. OH2 plus. All right. So got a little messy there. Sorry about that. All right. Now we're gonna. We've moved on to the second step. Remember, the second steps are or second page of that was protonation, loss of water, nucleophilic attack, and then deprotonation. So we've done the protonation. Now let's do the loss of water. So we're going to lose that water molecule. All right, we're going to lose that water molecule. Look at all right, I'm going to put plus resonance structure down here. I'm not going to actually draw that resonance structure, but there is another resonance structure there. All right, so we've done loss of water. Now we're going to do the next nucleophilic attack. So we're going to take this other oxygen. We'll go from that, the electrons and the other oxygen, to that carbon, and that's going to give us our nucleophilic attack. All right, so we have a positive charge there, and this one's still neutral. We don't need those electrons anymore, but and so now our last step, deprotonation. And for deprotonation, again, we're just going to take our OTS minus. We'll go from that oxygen to this hydrogen, and we will get our product. All right. This is one of those mechanisms I want you to know. It's related to a lot of the other mechanisms we're going to look at, particularly in the next chapter. And so this is a particularly useful mechanism, so I want you to know it. All right, what about hydrolysis of acetals? Well, we can hydrolyze acetals. One thing, here, I'm going to go back to this page and show you something. One thing that I did not indicate is that every single one of these is a reversible step. So that is a reversible step. This is a reversible step. Reversible, reversible, reversible. So every one of those is a reversible step. There's nothing in there that is irreversible. Like we don't lose some gas or something like that. It's always going to be a reversible step. So since it's always reversible, we can convert from the acetal back into the carbonyl compound plus the alcohol simply by reversing the conditions. And by reversing the conditions, what I mean is by adding a large excess of water. So with a large excess of water, you can drive the reaction back to your carbonyl compound plus your alcohol. And so, so you can do that. You can do sort of go the reverse direction. And so like in the Dean-Stark trap that we talked about earlier, we were removing water. If we purposely add extra water, we can make it go back. So let's look at number 29 just real quick here. Oh, and before we look at 29, I do want to mention something, all right? So here, if you're trying to identify, well, what's the alcohol and what's the carbonyl compound? Well, find the carbon that has two OR groups attached, so that has two oxygens on it. And if you can imagine, just sort of draw a line here to represent where you're going to cut it. And so these two OR groups are going to become the alcohol, and the carbon that had the two OR groups is going to become your carbonyl, either your ketone or your aldehyde. So in this case, we would clip these off. This will become a carbonyl, and then this will become that ethylene glycol. So let's look at number 29 and go through this process. So again, you're looking at it and say, ah, there's the carbon with the two oxygens. So if I can just imagine kind of cutting that, all right, and so when we do that, we treat that with the aqueous acid, and I'll just put H3O plus. We are going to get acetone, which is the carbonyl there, plus 2 CH3OH. So you'll get that. All right, on this one here, that's the one where we're going to break it. So we'll have H3O plus, and we will get, again, acetone in this case, because that is the carbonyl. And then our alcohol is going to be 1,2-cyclohexanol. So we'll get a 1,2-diol. All right, on this one, again, just find that carbon that has the two oxygens and kind of just draw a little line there. And this is not part of the procedure. It's just kind of a way to help you think about it. Again, with the aqueous acid. And we will end up getting 1, 2, 3, 4, 5. So we'll get that as our ketone. And then our alcohol, we'll get 2 of these ethanol. So 1, 2, we'll get 2 equivalents of that. All right, one more here. We'll chop that off. I'll go ahead and draw that H3O plus. All right, so that will become our ketone. And then our alcohol is going to be this 3-carbon chain. So HO, 1, 2, 3, OH. And so that is how we do that. All right, so now let's talk about acetals as protecting groups. How do we use acetals as protecting groups? We talked about protecting groups back in the last chapter. We took alcohols and we used silyl ethers, in particular tert-butyl tert-butyl dimethyl silyl ether, TBDMS. So we use the silyl ethers to protect alcohols. However, sometimes we may want to protect aldehydes and ketones. All right, we'll know that some of the reactions that we do on esters and acid chlorides and carboxylic acids are similar to the reactions that we do on aldehydes and ketones. And so some of the reactions will still work on, they'll work on both. And so let's say, for example, that here we've got, we've got this compound that has both a ketone and an ester. And our goal here is that we want to use lithium aluminum hydride to reduce this ester all the way to a primary alcohol. However, if we use lithium aluminum hydride on this, the ketone is going to react first with that before this one even does. So we're either going to just reduce the ketone first, or we'll reduce both of them. So if we reduce the ketone first, we're going to get this. It's the wrong compound. We want to preserve the ketone while reducing that ester. So the way that we can do this, the trick that we can do, is we can protect that ketone. So let me show you how. So we call this a protection, run the reaction, and then deprotection protocol. So to do this, we can take something where we have both, and I'm going to use that same compound, where we have a ketone and an ester, and we can protect that functional group in the form of an acetal. So we form that acetal, and so now this particular functional group, the acetal, is not susceptible to the reduction conditions of lithium aluminum hydride. So lithium aluminum hydride won't be able to mess up our carbonyl. All right, so we can use the LAH, the lithium aluminum hydride, to do the reduction, convert that ester into a primary alcohol, and then we just carry out the deprotection, right? Remember, acetal formation is reversible, so if we just add water with some acid, we can deprotect, and we end up getting that carbonyl. So protect, carry out the reaction, and then deprotect. So protect, carry out the reaction, and then deprotect. We're going to look on number 32, we're going to look at something that is similar. It's different, but it's similar. It's related. All right. We're going to have both a ketone and an ester, but instead of doing a reduction of that ester to form a primary alcohol, we are going to add a Grignard reagent twice to this to get this tertiary alcohol. And again, we saw this back in chapter 17, so if you need a little refresher on that, you can do that. But we're going to treat this, we're going to protect our ketone, because the ketone is just as reactive with our Grignard reagent as the ester is. In fact, it may even be more reactive. So we're going to take the ethylene glycol, so HOH, and the toluene sulfonic acid, and then protect. And when we protect, we will end up getting this acetal, but our ester will remain unaffected. All right. Then we can treat that with two equivalents of CH3 MgBr. You could also use an organolithium reagent like CH3Li. That would work as well. And then treat it with water. So we do need two equivalents because we're trying to add two methyl groups to that carbon. All right, and when we do that, and we have the protonation in there, so we still have our acetal. But we now have this. And then we can just hydrolyze this with H3O plus, and that will give us our desired product. Pretty cool. All right, so let's talk briefly about something that's called cyclic hemiacetals. We already know hemiacetals are halfway to the acetal, where we have OH and OR. All right, so a cyclic hemiacetal is one where the half part, the OR part, is actually in a ring. And so it comes around, makes a ring, and we have an OH. That's sticking out, but we have a ring that forms part of that acetal. And so that is the key component, is that our OR group needs to be part of the same ring. And you may think, well, all right, how useful are these? Well, these happen in nature all the time, and I'll show you examples of that here in just a bit. So how does it work? Well, when we have the cyclic hemiacetal, we get that from intramolecular cyclization of the hydroxyaldehydes. I'm going to show you the mechanism in a minute, but if you remember the mechanism for forming a hemiacetal, which is protonation, nucleophilic attack, deprotonation, then you already know this. Anyway, here we have a 5-hydroxypentanal, and here we have a 4-hydroxy. If we have a 5-hydroxy group, we can form a 6-membered ring, and if we have a 4-hydroxy butanal, we can form a 5-membered ring. Now, this does work better with aldehydes than it does with ketones. So we will get better formation of this when we use aldehydes over ketones, and the 5 and 6-membered rings work better than smaller or larger rings. All right, but the key is that because the OH, that nucleophile, is in close proximity, we end up getting very good yield of these. Are very good. It's not so much yield. It's very high percentage of it is in the form of a cyclic hemiacetal. So it increases the probability of our reaction, and we're more likely to remain as that hemiacetal, the cyclic hemiacetal. And you'll see these percentages are 90%-ish. All right, so let's look at the mechanism. Again, if you remember the mechanism for forming a hemiacetal, a cyclic hemiacetal is the same. The only difference is that our nucleophile is part of the same molecule. So protonation, nucleophilic attack, deprotonation. First step, protonation of the carbonyl. We protonate that carbonyl, get the resonance stabilized carbocation. We're not even showing the other resonance structure here. Our intramolecular nucleophilic attack is our second step. So the intramolecular nucleophilic attack, and we end up getting this as an intermediate, which we just need to deprotonate, and we form our hemiacetal. All right, so that is how we do it. Because this is intramolecular, we get much higher percentages of the hemiacetal than we would with a regular hemiacetal. So the intramolecular helps quite a bit. Quick word about stereochemistry, and I'll tell you why we mentioned the stereochemistry, because there are a lot of molecules that have stereochemistry when we start doing these cyclic hemiacetals. But let's just mention this real quick. So we can get intramolecular cyclization of this to give our hemiacetal, and you'll notice that we have a new stereogenic center. Since the molecule that we started with was achiral, and I've said this many, many times, if your starting material is achiral, that means that your product is either going to be achiral or a racemic mixture of enantiomers. Since we do create this new stereogenic center, we're going to have a racemic mixture of these two enantiomers. So just something to remember. If we do have a chiral component over here, we will not necessarily get a racemic mixture. And in fact, I'll show you what happens when we get to the section on carbohydrates at the end. So what if we convert a cyclic hemiacetal into an acetal? Can we do that? Well, if I wouldn't have this slide if we couldn't. So we're going to take a cyclic hemiacetal and convert it into an acetal by treating with an acid and an alcohol. The mechanism for this is exactly the same as the mechanism for converting a regular hemiacetal into an acetal. The only difference is that our acetal component here is it was intramolecular to start with, but we can do this. So this is just like that, and I think I've got the mechanism. I do. So the 4 steps. Before I do it, the steps are protonation, loss of water, nucleophilic attack, followed by deprotonation. So protonation of the OH group. So we protonate. All right, we form that H2O+. H2O+ is a good leaving group, so we can have water as a leaving group. That gives us this resonance stabilized carbocation. That carbon is susceptible to nucleophilic attack by our alcohol. And so we end up getting a positive charge here on that carbon. And the nucleophile comes in and attacks. And then that leaves us with this intermediate that just needs to be deprotonated, and we can form our acetal. All right, so there is our cyclic acetal. Pretty cool. One quick note about this. This is sometimes confusing. What if there is another OH present? Is that going to affect it? And the answer is not really. So if you happen to have, like if we want to convert it into an acetal, if you happen to have another OH present, that OH is unaffected. And it's not that it doesn't get protonated. Oh, it does. It gets protonated. It's that we don't lose that OH. We don't lose that OH to form a carbocation. The reason that this one is the one that gets affected is because we can form that resonance stabilized carbocation that's lower in energy than a regular carbocation. So we can do our acetal formation, and it works on this OH, but it doesn't affect the other OHs. So if your compound has both, it will be unaffected. So let's look at both 35 and 43. It'll just take a few minutes to do this. All right, so on number 35, here we are going to form an acetal. So here we've got ethanol, we've got our acid, and so we're just going to replace that OH with the alkoxy group. So all right, so we get that, and we can specify plus water if we want to get specific. And as I mentioned a little bit earlier in the presentation, if we have other OHs, those are unaffected. So these OHs will remain OH, and then this one will be converted into the acetal. And again, we'll have plus water if we want to get the full picture there. All right, so now we're going to look at sort of the summary of this whole chapter. So draw the products for each of these. And the main purpose of this, I'm going to encourage you to do this before I go through and do the solutions. And so the main purpose behind this is to help you remember these. So try to do this on your own and then come back and watch the video, or finish the video. All right, now that you've done it, you can check your work, right? I assume that you've done it. Okay, so here we're going to form an imine because we have a primary amine and an aldehyde, and it's in mild acid conditions, and that's either going to form an imine in this case, or down here it'll be an enamine. All right, so we got that. Oh, there. So this will be hydrogen there, and then we'll have the cyclohexane group will be there. So we will get that, and if you want, you could say plus H2O. All right, here we're going to form an acetal, and it will be a cyclic acetal. All right, that methyl will be unaffected, and of course plus H2O if we want to include that. Here, this is hydrolysis of an imine. So you can kind of think of it like, oh, we're going to hydrolyze that. So this will be our carbonyl compound, which will be the butanone, and then this will be our amine. So 1, 2, 3. So we'll get that ketone, which is a 2-butanone, plus 1, 2, 3 NH2. All right. Here we have a secondary amine plus an aldehyde. It does have an alpha hydrogen, so we can form an enamine here. So I did not mean to draw a double bond there. I was thinking imine. All right. So we'll do C6H5. And then the nitrogen, we'll put that ring on it. And we'll get that double bond there. Oh, we need one more carbon there because there's 2 carbons adjacent. So we would get this as a product and H2O if we want to keep track of everything. All right, this is the one we saw earlier that is hydrolysis of hydrolysis of a cyanohydrin. And so when we do hydrolysis of this, we're just going to get that as a carboxylic acid. So we'll convert that cyano group into a carboxylic acid. So this will still be OH, but this will be COOH. So COOH. All right, this is a cyclic hemiacetal that we are converting into an acetal. And of course, we could do the plus water if we would like. I didn't do the other products on this. It's complicated, so I'm just going to say we get a carboxylic acid, but we do get some other stuff like some. We get the ammonia off from that. All right, here we're going to do hydrolysis of an enamine, and so we're going to break this. This is going to become a carbonyl. We'll get rid of that double bond. This will become a carbonyl, and we will get that secondary amine. So that will be our carbonyl compound, and then nitrogen, hydrogen. We'll get that cyclic amine. That's a nitrogen, by the way. It's getting worse by me messing with it, so I'm going to leave it alone. And then finally, we get to finish on one of my favorites, which is a Wittig reagent. So a Wittig reaction. All right, so we're going to form, in place of this, we're going to break this apart and break this apart. We're going to form an alkene. Let me count the carbons here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, we'll get that plus triphenyl phosphine oxide. And remember that triphenyl phosphine oxide, that is the driving force for this whole thing. All right, that is the end of the in-class assignment. We do need to go back and just ever so briefly talk about carbohydrates. So this is a very brief, ever so brief introduction to carbohydrates. It's a mention of carbohydrates because we just talked about cyclic hemiacetals and cyclic acetals. Let's mention this. So carbohydrates are sugars, right? So they're sugars, starches, any number of things. Many of them are super delicious. But we're going to take those carbohydrates. We're going to look at them. We're going to find that quite a few of the monosaccharides, not all of them, but quite a few of them have a cyclic structure to them. So this is glucose, and glucose, you can break this apart and you can have what's called the aldehyde form of it, where it's a straight chain. But here it does spend most of its existence in this form where we've got a hemiacetal. So here we've got a hemiacetal in this, and it's quite stable because it is cyclic. So they'll contain these hemiacetals, or some of them will even contain acetals. And if we look over here at lactose, on lactose, it's made up of it's a disaccharide. It's made up of 2 saccharides, so 2 sugar units. One of them over here on the right is a glucose. You can see this looks just like this. And the one over here on the left, it almost looks like glucose, but it's one carbon, has a different stereochemistry, and that is this right here. So instead of going this way, it goes this way. Well, that means this one is called galactose. So that's galactose, this is glucose, and they come together to make lactose. So glucose and lactose are examples. You'll notice this one has both an acetal and a hemiacetal. All right, so the 6-membered rings are preferred, and so are hydroxyaldehydes. So if we have a 5-hydroxyaldehyde, it can come around and form a cyclic 6-membered ring, and that's what happens with these. So if we get cyclization, that OH that's in the 5 position, so there you go, there's the 5, it comes around and makes an acetal, or I'm sorry, hemiacetal formation. So we get the hemiacetal formation. So it attacks this carbonyl, and we get the hemiacetal. Now, because we're creating a new stereogenic center, we're going to have some interesting stereochemistry occur. There's two possibilities for this. One possibility gives you this, which is the beta D-glucose, and then the other possibility gives you the alpha glucose. These, I want you to think for a second what kind of isomers these are. All right, do you have a chance to think? All right, these are diastereomers of each other. You'll notice that we have all these stereogenic centers that are identical, and we have one that's the same. And for diastereomers, if you have at least one that's the same and at least one that's different, those would count as diastereomers. So these are diastereomers of each other. You'll notice we don't get a 50-50 mixture here because our starting material is not achiral. It is a chiral molecule. So we can get one of these preferentially over the other. All right, well, that is the end of chapter 18.